Okay, so here we are going to talk about the heat. Sorry, this is the heat equation, not heat heat equation. Okay, we are going to talk about the heat equation on an interval from 0 to L. Okay, so let's go now and let's solve several initial boundary value problems on this interval. We're going to take only two different boundary conditions. Okay, the first case where that the ends kept at temperature 0. So both ends, if we have the bar from here, okay, x equal to 0 and x equal to L. So we are assuming that both ends, their temperature is going to kept at 0. Okay. If the initial temperature in cross section at x is f of x and the ends of the bar are kept at temperature 0, the problem for temperature distribution function is going to be like this. Our problem, in order to solve it, we're going to find that this is the heat equation, as we know, and this is going to be true along the bar length from 0 to L at any time t, right? And our condition is u of 0 and t, the temperature at the left, equal to the temperature at the right, x equal to L, equal to 0. Both of them, they are equal to 0 for any value of t equal to or larger than 0. Okay, and in between, along this bar, our function of the heat along this bar is going to be u of x and 0 at the initial condition at t equal to 0 equal to f of x, any function of f of x, something like this, for any value of x between 0 and L, including them. Okay, we are going to derive, there is a derivation here. Okay, no need to go through the derivation, just I want you to take care of the final equation. But if you like to go to the derivation, you can go through it, and you are going to find that using the Fourier sine expansion that we have already explained before, using it, we can derive our solution, which is going to be u of x and t at any x and for any value of x and for any value of t, it equals to 2 over L, the summation of some terms from n equal to 1 to infinity, the integration from 0 to L, f of z, sine n pi z over L dz, like we have transformation of variables here, then sine n pi x over L e raised to the power minus n squared pi squared k, which is a constant, times t over L squared. This is what we call it the solution of the heat equation for the case of this boundary condition. Okay? Okay. So this means that actually our equation is going to be something like this. We're going to say like ux of t equal to like the summation n equal to 1 to infinity, okay, times cn, okay, summation, yes, cn times sine n pi x over L times e minus n squared pi squared k t over L squared. So this cn, we use it as a coefficient that we're going to like define it in the beginning, because this, it has the integration actually. So cn, the coefficient that we're going to use for the solution of our heat equation, is going to equal 2 over L, the integration from 0 to L, f of z sine n pi z over L dz. This is what we should always use in the beginning or define, and then we can solve our equation. Okay, so now let's jump directly to an example so that it is going to be easier for us to understand. Okay, suppose the ends are kept at 0 temperature. Suppose that we have a bar and the ends of the bar, they are kept at x equal to 0 and x equal to L. They are kept at what? Exactly 0 temperature. So T here is 0 and T here also equal to 0. And the initial temperature, look here, the initial temperature is going to be described by a function, as we said before. It is going to be f of x. But we found that this function is what? Is a constant, given here in this example to be a constant. So we're going to find that something like this. Okay, this is the function at the initial temperature. Okay, means that at t equal to 0, which is constant. So we are going to compute, let's go back. The first thing is what? Exactly, Cn. We want to compute this Cn first. This integration, we need to use it and define it first. So our Cn equals to 2 over L from 0 to L, the integration of f of z. It is a constant here, right? Because the function is constant. Sine n pi z over L dz. This is limited integration and easily you can obtain this integration as 2a over n pi times 1 minus 1 raised to the power n. So our solution, what is the meaning of solution? Exactly, the heat at any point x at any time t equals to 2a over pi times 1 minus 1 raised to the power n over n, to this part here we put it, okay, which is Cn, and then sine n pi x over L times the exponential term. Similar exactly to what we have said here, right? This is here what we have said here. This is the solution of our equation, right? Okay, so now this term, if you are going to look to it, you are going to find that it equal to if n is odd and it equal to 0 if n is even, right? So we are going to what? To omit the even terms because it's going to be 0. It will not add anything to our summation, right? So we are going to omit it and we are going to rearrange the whole equation in order to make it better. So for the even terms, we're going to neglect them because they are 0, and we are going to take only n as odd. So how we can do this? So we can omit the even values of n in the summation to write the solution as, this is our solution. So in our equation, this is going to be omitted and we are going to use 2 because we are going to have it as the odd values only. So it is going to be like 2 here times 2 outside, they are going to give us 4. So it's going to be 4a over pi. And then this n is going to be what exactly? This n is going to be what here, and this n also? Yes, something that is representing the odd values. So if I put it like 2n minus 1, does it work? Yes, it will work. Let's assume that n equal to 1. So this value is going to be 2 by 1 minus 1, it is 1. And in case of n equal to 2, so 2 by 2 minus 1 equal to exactly 3. It's the odd value. N equal to 3. So 2 by 3, 6 minus 1, it is 5. And so on and so forth. Okay, so this term is really giving us the odd terms only. So we put it here, we removed this part which is only giving us 2, and we replace every n with 2n minus 1, as you can see here in the solution. This is 2n minus 1 and everything is the same. Okay, so this is considered to be our solution. This is considered to be our solution. What is the meaning of the solution again? Exactly, we can describe the temperature at any point across the bar, okay, at any point because this is the x-axis. So at this point we can express it, and at any time, so this means that we can give it at any time with knowing of x. Okay, with knowing of x and t, and you can find here this is t here. So if we know x and t, and of course we know L, the length of the bar, this is known, and the number of terms that we want to take, like 5 terms, 6 terms, 10 terms, 20 terms, how much, then we are going to give exactly, okay, we can give the solution of our equation, okay. So this is the video for today. I hope that you have understood it well, and I hope that you can follow this only for the case of both ends are kept at 0. As we said, both ends, they are kept at temperature of 0. Okay, thank you, and see you in the next video.